Well, thanks everyone for stopping by. And this is I've done a couple of these um, Smart Hub talks, and this is by far the biggest turnout that I've ever had. So thanks. This is really great. I talk about automotive a lot, and it's probably because we're in Detroit that people are really interested in this topic. So, thanks. I appreciate you stopping by. I'm here. I'll take any questions during this presentation. First off, my name's David Tucker. Work with HP. I'm our automotive development lead. I manage a small team of engineers that help people adopt additive manufacturing for automotive product development. My background is kind of unique in this space. I'm a plastics engineer by training. There's a couple other here in the crowd. Went to Ferris State. Any Ferris State grads here? Yeah, okay. And I've worked pretty much half of my career in the automotive industry developing high volume manufacturing products inside of cars. So, by show of hands, who has worked on an automotive program for a pretty good crowd here? Okay. So after joining HP and joining Multijet Fusion on our team, our focus is to get into this market and to help people utilize our tools to design applications for this market. So we're going to walk through some of what it actually takes and how do you utilize our tool to be able to do just that. So I'm going to go over a couple things. So I like to start kind of laying some shingles first. And first is talk about the process. We'll talk about some science. Science is always fun to talk about, so we'll do some of that. And then we'll talk about product value, like how do you utilize Multijet Fusion to actually achieve product value inside of the products that you're working on, or that you could work on. And then finally, we'll influence this of the importance of the process engineer. So although we have digital manufacturing technologies, how does this process engineering part focus into that, and how do our organizations need to evolve to embrace this type of role? So first start, from a basic architecture standpoint, Multijet Fusion Systems. Who, by show of hands, how many people have seen this piece of equipment? Okay, pretty much that's about half. We're getting a little better. A couple more people here. We're just located right over there. If people want to go and see it. I wish I could have brought it over here so people could have saw it. But basically, we have a printer, we have a processing station, we have build units. Those build units shuttle between the printer and the processing station to basically enable continuous uptime of capital investment. Right. So it's about the printer. It's about being able to continuously print things. And when you make an investment in a company, that investment should be utilized continuously. That enables manufacturing. So from an architecture standpoint, the enablement of manufacturing is built into the core of this. So knowing how it kind of functions, let's think about the process of how it actually works. So there's 4 steps to our process, and at the core of it is our thermal inkjet technology. So our thermal inkjet is basically we deposit. It's the same inkjet heads that you would be depositing, printing on 2D paper, modified a bit to print on plastic powder. That's then fused and melted, and how we get mechanical strength. So how that process works is really 4 steps. We first start with the material spreading operation, where we spread a layer of powder, and then with one continuous pass, we deposit 2 agents on top of that powder using our thermal inkjet heads that we had previously discussed or shown. Depositing 2 agents. One is a fusing agent, one is a detailing agent. Okay, one of them is black, the other one is not. So if you, and then after that, we then expose that with an area-wide infrared energy source. Does anyone know what happens when we have the infrared energy source and we have something that's been printed black? What would happen to the black thing if it's exposed to light? If something's black and you have a really bright light, what happens to it? It gets hot, right? So we are managing this process so that when we print something, we want to expose just enough energy so that we take that plastic powder that we printed on and turn it into a liquid. Right? Take that plastic so that it turns into a liquid. It changes phase from a solid into a liquid, right? So that we actually can create structure inside of that part, right? Inside of the thing that we printed, and then we end up with a fused part. So that's the fundamentals of our process. I'm a believer that if you don't understand the fundamentals and physics of something, there's no way you can ever get into production with it, right? So understanding the physics of what's happening on a small scale, and we'll dig more into this, really helps us, understand and be able to use the tool. So if the black material here that we talked about melts, what does the other one do? What does it do? It stays solid? Okay, well, that's really, really close. So it evaporates and creates a thermal fence on the side of the part. So here you're creating basically thermodynamic reactions, right, where you're melting some parts and then you're controlling the temperature of the others, right? So to do that, let's talk about some of the science. What does that actually mean? So we understand the science, the process. Let's talk about some of the science that enables that. So basically what we're doing, by doing this, each layer, we're trying to molecular entangle with the layer above it. So by doing that, by getting molecular entanglement, we're enabling mechanical properties, right? Mechanical properties are why plastics work, right? Plastics are long chain molecules, and they entangle with each other, and that entanglement gives us strength and gives us stiffness and gives us those kind of things, right? So with our process, we're basically trying to improve molecular entanglement. And to do that on every layer, what we're trying to accomplish is when we print an image, if you look at this pattern in the center, we're printing an image and that image is black, right? And when we expose it to overhead energy, which is in this image, those top lamps, we're basically trying to make sure that the black material is above the melt temperature or the phase transition point of that material, but the powder stays below. That kind of makes sense, right? So we're trying to molecular entangle only the stuff that's printed. And so to do this, we have really, really complex software on top of it that takes the thermal image in between every single layer and validates, yes, I melted. Yes, I've achieved molecular entanglement. I have mechanical properties, right? So every layer, this is happening. And so understanding that process, then we can start to say, how do we actually use it? And how do we use it when we're making cars and car parts to make them better, right? So let's walk through some of the different application spaces. Traditionally, and I think we all know this, additive manufacturing is really great for prototyping things, replicating a design, right? So we're a replicating process. I want something. This is a world that, the version that's going to be additively manufactured and the version that's going to be done in mass production, we want them to be the same or at least look the same. So another area, spare parts, right? So, something where, so we don't need a whole lot of them. We know there's an economic constraint to being able to produce things at scale, or maybe with mold setups. Additive manufacturing really makes sense there. One of the interesting areas for us is looking at this low volume production area. It's like, well, how do we actually take something into production and enable that item to actually be used inside of an end item use case? Our best public example of that is the BMW window rail guide. So this little part here that's on the side, it's over at our booth too. You can go and take a look at it. As a low volume vehicle, right? It makes economic sense, right? The whole base of that space is based around something that economically makes sense. Like, it looks the same, it functions the same, right? But it costs less. There's situational economics there, right? What's interesting in the automotive space, though, is that there's never been a solution to actually address that space. So if I drew a bell curve that represented volume, and then I would have to minus out this other space because there was never a solution there, right? So the fact that people are getting into additive manufacturing is actually enabling a solution in the space that never existed, right? And multi-jet fusion is, in other technology, are really prone to filling that space as people understand how the processes work and how to actually design with them. When we move up inside of this zone, we really want to start unlocking different levels of value, right? So different ways that we can get value out of our additive manufacturing processes to actually enable improve performance. So what does that performance look like? It could mean lighter weight solutions. It could be personalized or customized solutions using unique textures. It could be optimized fluid management systems. It could be faster time to market. It could be energy absorbing structures. These are all things that we're not necessarily designing for today, but we can create the systems and tools to be able to do that. And some very specific examples here, we can look at improving product performance, how to design for mass production, how do we accelerate product development, and then finally creating something really unique, right? Like how do we go about doing that? So to walk through a couple of these, we have some different examples that are really from HP's vast portfolio of products, but really correlate and resonate and transfer over to automotive product development. So the first one is looking at optimized fluid management systems. When we take a look at this one, we have one, on the left-hand side, a multi-jet fusion part that combines a whole bunch of parts together. Economically, this makes sense, and in low volume, this makes a ton of sense. So it's like you're basically, by combining parts, you're eliminating tools, you're eliminating assembly functions, you're eliminating testing equipment. So getting a lot of different levels of value. But you also get a performance improvement, because when you look at different manufacturing processes, those manufacturing processes come along with them, you get manufacturing constraints. So with traditional processes, you have constraints of adding draft to parts, right? Who in here has had to add draft to a part before, right? It's pretty standard. So with our processes, you don't necessarily have to do that unless there's a functional reason though you want to add draft. And then also with injection molding, there's limited sizes that you can actually flow material through. So our additive manufacturing process doesn't have that constraint. So it's not like a minimum flow path, for instance. So, additionally, when you look at design, there's different ways that we can look into designing mass out. So designing parts that weigh less, and therefore drive fuel efficiency or drive different things inside of vehicles. So anything that really is moving, you can look at it really through three different lenses. The first lens is really looking at saying, well, how do I just replicate a tool, like replicate the process, making a block like a duplicated form, right? A replicated form. And then you can take one step further where you look at optimizing and we look at adapting that design and saying, well, what can I do to that part to make it more friendly for that process? And as you learn, you can take a really big leap and say, well, how do I completely optimize for that? How do I actually look at the loads and use the minimum amount of material and design for that process? And what I think is important here is when you take a step approach, the things on the right-hand side, like these types of designs, are really organic and look awesome, right? But they're really hard to actually do unless you have software and the manufacturing tools. So by jumping far to the right-hand side, you're basically putting a lot of things in front of you saying, well, I have to change this and this and this to be able to do this. So I like to take small steps, right? So it's like, well, as you start adopting something, look at small steps and growing that adoption and growing those use cases as you gain and learn on the tools that you actually have. So one of the ones I find most interesting is actually when we talk about accelerating product development. And this is probably one of the most interesting examples. And hidden in here is the way that, and if anyone's thinking about additive manufacturing, should be thinking, right? Should be thinking about adopting a strategy that makes sense. So here, the strategy makes sense saying that I'm not making everything out of a 3D printed technology here, right? I'm only selectively picking it, and what I'm doing is I'm taking all of the complexity and I'm putting only the things that are complex in with a advanced technology, because advanced technology are inherently expensive, right? So by doing this, you can start developing strategies for saying, well, how do I create systems inside of vehicles or systems inside of products that enable a low-cost economical solution. So for instance, if you're working on like a ducting system, right? Maybe you only print the joints, and then you use standard tubes that connect all those joints together, right? Or if you're so it's like take the complexity and put it only where you need it. I only need the complexity in the elbow. I only need it in the manifold. I only need it here. And adopting those types of strategies, those start to have ripple effects inside of your organization, right? And you basically accelerate product development. And you do that by changing the critical path. So who in here is a project manager? Okay. There's got to be more project managers than that. Okay. Now everyone's lying. Everyone's managing projects somehow. Has to be, right? I'm a certified project manager. And one thing I know is like, well, you have to remove the critical path. So how do you do that? It's like, well, by taking out everything that has a long lead time, right? So for us, take out tooling. And what does that end up doing is it enables you to go through the part design process faster. But the thing we all have to be aware of is that the first time that you go through something new, you're going to have to go through it once, twice, maybe 3 times, right? So when you first start adopting for production and trying different strategies, give yourself the time to learn inside of your organization and to enable a solid production strategy. Okay. Another topic, and I think that this is something that recently I'm really interested in talking about. I love to kind of just, when I learn something, just start to talk about it. But printing of textures. Does anyone in here print textures on parts? So there's a couple of people. It turns out they're included. Like, you can get them for free if you plan for it. And I don't think a whole lot of people recognize that and plan for the fact that parts can look really great out of a printer, right? And so thinking about the workflows and thinking about how you actually do that matters, right? And so as I started to learn more about this and the different tools that people are using, for me it's become really important to talk about and to really challenge people to think about when they're making something, put the texture onto the model, right? And think about how you're actually going to get the texture on there and make the part look awesome, because textured parts look awesome. There's some at our booth. Check them out. They look really great, especially if they're coupled with paint. They look like final parts. It's pretty amazing. But looking through some of this process, it all starts with creating a bump map, right? And taking that bump map and applying it to the part. You can use different types of softwares to do that. You can use SolidWorks, you can use Rhino, you can use Blender. There's lots of different tools that do this, right? And people need to start thinking about that. And what's cool is that you can start looking at inspiration from different things that have texture. You can take pictures of different rock formations, right? Or different types of things, turn them into grayscale and apply them to parts, right? You can take pictures of like artwork and do the same thing. All really interesting things, all adding value to parts and creating value in a very unique way. I'm really fascinated about this lately, so I talk about it all the time. So anyway, here's an interesting example where you're actually taking a structure, a generative design minimum component, and actually seeding a part on a surface to create something that's completely unique and random. So future in vehicles, future in product development is actually doing generative design for how things actually look. So last point, last couple slides here actually, is with all this, there's still a continued importance for having a process engineer, right? Having someone that looks at a design before you print it and optimizes that design and thinks about the outcomes of that printer and that manufacturing process and make sure that you're planning for positive outcomes, right? And so from that, I'm an advocate looking at the design and knowing how to actually optimize for that. What's that design for manufacturing, essentially? So there's a couple different points that I like to impart in people. Really three things I like, three things to think about. I've designed about 1,500 molds in my career, and it wasn't until I started using additive manufacturing technologies and I thought I was a design expert that I realized how to actually design for injection molding. Now I like to associate the two together and talk about design choices between one technology to the other technology. I like to use injection molding because I think that's what we're competing against. We're competing against a cognitive mindset and people designing for traditional technologies. So with that being said, the first thing that I do when I'm designing an injection mold, if I have a part, what do I do to that part? I have it listed here. I identify the die draw. Why do I do that? Why do I need die draw? So the part opens. Part's got to come out of the mold, right? So when you're designing a part, it's like, how does that part actually exit the mold? Once I determine that die draw, I design all my features around that. Okay? For us, really identifying the build direction. What direction are we going to build these? I mean, we tend to think things are isotropic, but they're not. They're anisotropic dimensional properties here. So let's optimize for those. Okay? So doing that first step, identify the build direction. For us, it's taking all of the small features of size, like your bosses, your different openings, and making sure that they're all printed inside the XY plane. So what does that mean? It means when you're designing a part, identify a threshold or outcome that you're looking to achieve. Okay, that threshold or outcome can be based on, affordability, surface finish, tolerances, some just different examples here. Now, as you rotate a part in different orientations, you're either going to add to that threshold or take away from it. So us understanding how we move a part in those dimensional outcomes that we're going to be achieving are important for us all to study and to understand, right? So the next part, when I look at an injection mold, the next thing that you look at after you identified that the mold opens, okay, does anyone know what the second thing you think about? I'm going to wait. It's like, can the mold fill, right? Can I get plastic from one end to the other? Well, it turns out there's no plastic filling inside of any of these additive manufacturing processes, so we shouldn't be thinking like that. So I had this, this realization that all of this extra material inside of this part on the left is all waste. I don't actually need it, right? It's there because I have to get material to flow from one side to the other. So from our design, start taking all that stuff out. We have some interesting examples of it. They're remnants of an injection molding mindset, right? We got to get rid of them, right? And so, and why do we need to do that? So the second step, we're basically saying with this constant wall thickness, we're saying that the physics of this process has some sort of outcome on the quality of those parts. For our process, it's actually the same statement. The physics of the process, meaning the amount of energy I'm absorbing layer by layer by layer, is going to have an outcome on the quality of the final part. So, doing that, when you start looking at ways that you can take a design and manage the physics and design in for the proper physics on a layer by layer basis, is how we're going to get to outcomes. So, for instance, here, if you take a look at this, is just a typical box. It's a little box, maybe it's a cover for something. How many in here have made a box before? There has to be a lot of box makers, right? Little covers for things, okay? Well, if you design it the way that we would design an injection mold, right, you would be printing little outlines, and then when you got to the top, you'd be printing a really large black area. That black area is going to absorb a lot of energy because we melt on an area-wide basis. That area-wide basis is going to cause more shrinkage in the top, is going to make the part warp, right? So when you're doing this, being aware of that physics of that process, and take the design, and maybe you add a dome to the design. So if you take a look at this little work stream here, where you're printing an outline, you're just printing different variations of an outline as you build those parts up, having a constant physics, thermal reaction as you're building it. Or look at corrugations. I love corrugations in all plastic design. So I recommend everyone doing this no matter what they're doing, but corrugations are a great solution for managing thermodynamics inside of our printing process, and they give you really rigid parts. So something people should be doing anyway. So the last item is when you think, when you think about injection molding, the last piece is, we always ask ourselves, like, first it was like, did it open? Second, can I fill it? The third, what's the question that people ask? Anytime you're going to make something, well, how much is it going to cost, right? That's pretty good, right? How much is it going to cost? So with injection molding, it's all about press size, right? How much? What's my press size here? How do I optimize my cavitation inside of my tonnage? For us, it's thinking about packing density. Still, it's an economic question, right? How much is this part going to actually cost? And so, some interesting examples here. It's all about how many parts that you're putting inside of that build space, right? So we have a three-dimensional build space. You can put all different types of parts in there, as we were showing earlier. It's area-wide, right? So it relatively has the same amount of build time no matter what, right? So for us, the more parts that you put in, you actually affect the price per part, right? So here's an example where inside of our build space, we can only fit 3. And this is where we combine parts together. What we ended up doing is taking that same part and broke it up into 2 parts. And by breaking it up into 2 parts, we're able to fit 8. Right, so every time I make a build, I have 8 parts. So I have the effective cost of that is significant. I don't need as many machines or as much machine time to be able to make these. And this is an example where we actually took a part and are advocating for breaking it up. We're advocating for breaking it up because economically it makes sense. So thinking about that build space when you're designing and how many parts that you can actually fit inside of it leads to advantages. So, and those are the end of my presentation. If anyone has any questions, I'm more than happy to take them. And I hope you visit our booth. And yeah, thank you.